Hello, this is TheoryStation and I'm John Duggan. This program is Rational Choice Modeling. The series we're in is Basic Formal Theory Toolkit, and this is the 8th installment in the series. We've covered a fair bit of ground in the series. I'm really just trying to hit some of the most fundamental models that we use in mathematical modeling in economics and political science from my perspective. So we started with the preference and choice model and talked about the optimality principle. Then we went from there into cost-benefit analysis, and then talked about for quite a while about the one-dimensional policy choice model. What I want to do now is veer back into more sort of standard economics territory, and we're going to talk about the theory of the consumer. So this is the, let's call it the consumer model. Although, it sounds like this is straight economics, it's important for people who want to do political economy or political science modeling because, first of all, voters are consumers. But secondly, at the heart of this model is the idea of constrained optimization, which is something that goes far beyond just the consumer model. So there are lessons in this model that carry over to a much wider class of models and applications. So I want to talk in this installment about the consumer model. And so we'll have a decision maker who is a consumer. I won't explicitly model that person, but they're there in the background. As with previous models, I want to start with a set of conceivable choices for the consumer. Now, this is really the canonical consumer model, and the way we're going to think about it is this is a consumer who has to decide how much of a certain number of goods to consume. We're going to focus on the simple case of just two goods, and so the consumer is going to choose two quantities. We're going to let these quantities be real valued, so they can be fractional, which is a bit of an abstraction, but it's a useful one that allows us to use calculus techniques to understand the consumer's problem. All right. So what is the consumer's problem? We're going to assume the consumer has to choose quantities of two goods, and each good has a price per unit. Those are just taken as given, so they're exogenous. They're going to be parameters in the model, and the consumer has an amount of money that they can spend on the two goods. Then we have to specify the consumer's preferences, and we ask what is the optimal combination of consumption for the two goods that the consumer can obtain. Okay, so let's jump in with some notation. The set of conceivable choices for a consumer is going to be just pairs of quantities. We're going to assume that consumption is non-negative. So the standard notation for this, excuse me, would be to say the consumer has to choose non-negative amounts of each good. So R with a subscript plus means the non-negative part of the real line. And because the consumer can choose a pair, we're going to talk about R squared. So a particular combination of goods, of quantities, would be, say, an x1, x2 pair. I'll put a pair in parentheses. Again, here, x1 is non-negative, x2 is non-negative. And we will call this a bundle of goods. Okay. We'll come back to sort of the geometry behind this, but let me just continue with notation right now. So the price of good 1 is going to be P with a subscript 1. The price of good 2 is P with subscript 2. Let's assume that those prices are both positive, strictly positive, and again, those are just going to be taken as given by the consumer. Okay, and we will assume a non-negative budget that the consumer has to spend. B greater than 0. So that said, now we have to, well, let's think about now what's actually attainable for the consumer before we talk about preferences. So given a bundle, X1, X2, the cost of that bundle is the following. Well, if there's X1 units of good 1 consumed, the price per unit is P1, so the amount spent on good 1 is P1 times X1. Same for good 2, right? So the total cost of that bundle would be the sum of the amount spent on good 1 and good 2. Because of this budget, we're going to assume the consumer can't, borrow or, pull out their credit card. So the amount spent has to be within the consumer's budget. Okay. So this inequality here is called the consumer's budget constraint. And in just a little bit, I'm going to remove the inequality there and we'll just deal with an equality constraint. Okay. So geometrically, a bundle is a pair of numbers, so it's going to belong to the Cartesian plane. And we'll use the horizontal axis for the amount of good 1 consumed, the vertical axis for the amount of good 2 consumed. If you think about it, the consumer has B dollars to spend. If they spend everything on good 1 and nothing on good 2, the maximum they can spend is B over P1. If they spend everything on good 2 and nothing on good 1, the maximum they can spend is B over P2. And so, of course, they can choose they can choose bundles with positive amounts of both goods. This constraint here, P1 X1 plus. So let's think about the bundles where the consumer spends all of their money. So that would be bundles satisfying the exact equality. We can graph that if we solve for X2 in terms of X1. So that'll be B over P1 minus P1 over P2. Oh, I'm sorry. This should be a 2. X1. Okay. And so if we graph that relationship, what we get is, I missed my horizontal intercept there, but we get this line. Those are the bundles that cost all of the consumer's money. Of course, the consumer can choose not to spend some money. So the set of affordable bundles is this triangle. This is called the budget set of the consumer. And this corresponds to the feasible set that we talked about before in the model of preference and choice. These are the bundles that are actually available to the consumer. Okay. Now, preferences for the consumer. So I want to define preferences over this whole non-negative quadrant of the Cartesian plane. Obviously, there's an infinite number of bundles in that quadrant, so I can't write down a ranking. So what I can do is, I can just assume that there's some, a list, so to speak, of preferences, but you can't really list all those preferences, literally speaking. But we can assume that the consumer has preferences and can compare different bundles and say, oh, I prefer this one or that one. And those comparisons are going to be summarized by this P. But actually, it's also quite common to assume a utility function for the consumer. Again, it's not really adding much. It's just basically a labeling, an assignment of utility to each possible bundle, where better bundles have higher numbers. The utility function is going to be a function of the bundle consumed. So it actually has two arguments, x1 and x2. All right, and so given that utility function, we invoke the optimality principle, and the consumer in the rational choice framework is going to choose the best bundle that's available, that is the best bundle in this feasible set. What that means is they're going to maximize this utility function. Okay, so they're going to choose x1, x2 pairs such that the consumption of each good is non-negative. However, they can't spend more than they have, so they have to respect this budget constraint. All right. Now, it's pretty common, you don't have to do this, but it's common to assume that that goods are actually good. So if the consumer has more of the goods, they're better off. Okay, that assumption is called monotonicity. What that means is that if we solve this problem for the consumer, this inequality here in the budget constraint will always hold with equality. That is, it's never optimal. Assuming the consumer has these monotonic preferences, it will never be optimal for the consumer to just leave money unspent. Okay. There's no savings in this model. You can bet that this model has been extended to, multiple periods where you can save across periods. But in this basic model, there is no future. This is just, you have an amount you can spend today. If you don't spend it, it doesn't do anything for you. All right, what that means is that it's without loss of generality to just write the budget constraint as an equality. Okay, so this is a constraint optimization problem. It's different than what we saw in the cost-benefit problem because there we used calculus techniques. We drew on this first order condition from calculus, which allowed us to solve that problem. That problem was, first of all, one-dimensional, and this is two-dimensional. And the cost-benefit problem didn't have this constraint. It had an inequality constraint, but here we have an additional thing, this budget constraint. Okay, but we can still use calculus techniques to help us solve this problem. I see that I'm running a little bit late with this. Let me just talk about the consumer's preferences, and then I will defer to the next installment. So to go into the consumer's preferences a little bit more, we're assuming a utility function, right? So this function is assigning a utility to every bundle. Okay, this is a multivariate function. Unlike the cost and benefit functions that we saw earlier, this is not so easy to graph. We can graph this sort of thing, but I don't think we want to do it too often. The way I would do that is I would I'm going to use this non-negative quadrant of the Cartesian plane to represent the set of possible bundles. I'm going to take that plane and lay it flat. And, so these two axes I've drawn here, I want you to think of as kind of coming out of the whiteboard. And then I can use the vertical axis here to represent utility. Okay, so if I were going to graph a possible utility function, I could imagine something like the following. Let me do it in blue. So first I'm going to think about setting the consumption of good 2 equal to 0 and just increasing the consumption of good 1. And, for any consumption level of good 1, there's some utility that's determined. We can do the same thing if I set the consumption of good 1 equal to 0 and increase the consumption of good 2. It's going to generate utility. What about a bundle that has a positive amount of both goods? Well, I'm going to fill in the graph of this utility function like so. This isn't looking so great, but maybe you can sort of see it's like a three-dimensional surface, or rather a two-dimensional surface in 3D that's increasing as I have more of good 1 and more of good 2. So for a bundle like this one here, which has a certain amount of good 1 and a certain amount of good 2, we go up until we hit this graph over the, of the utility function over that bundle. And then the utility is going to be just this vertical height of the function above that bundle. So to read that off, what we would do is we would have to come back over here and then go back over to the vertical axis, and that would mark off the utility from that bundle. That is not, this is not a simple thing to do. You don't want to do it too often. It's okay to get insight, but really instead of doing that, what we would normally do is, instead of trying to graph utility, we would, instead of trying to graph this whole utility function, what we would do is really graph kind of a topographical map of this utility hill. Okay, so here's the, I've just drawn the non-negative quadrant that represents the set of possible bundles. And if I take one bundle here, just kind of randomly, let me give that specific notation, x1 bar, x2 bar. This utility function assigns a certain utility to that bundle, right? So u of x1 bar, x2 bar, that is a utility assigned to that bundle, and let me just save writing and call that u bar. So the utility from that bundle is u bar. Now, over on the in this three-dimensional picture, that that bundle, you know, it has this utility, but you can now imagine, what if suppose you were standing on that hill and you're right over this bundle, so your altitude is equal to the utility from that bundle. Now you can imagine walking around the hill in either direction and doing so to just maintain the same altitude, okay? The bundles that you're walking over are going to be something like, you know, it's going to be maybe a curve like this. And the utility of all those bundles is the same as U bar. It's U bar, okay? So, so this curve that you're walking over, we can write that in terms of, you know, standard notation. That's going to be the x1, x2 bundles such that the utility is equal to U bar. That's what this curve is. Okay, so right, those are basically all the bundles that have the same utility as x1 bar, x2 bar. Now, remember, we assign higher utility to better bundles, lower utility to worse bundles. Since these all have the same utility as x1 bar, x2 bar, that means that the consumer doesn't have a preference between them. She's indifferent over all those bundles on that curve, okay? So we call this the indifference curve through the bundle x1 bar, x2 bar. Okay. If we picked a different bundle to begin with, we could have done the same exercise, and there's going to be some collection of bundles with the same utility as that. And in fact, this whole quadrant is filled up with these curves. And again, they're basically just a topographical map of this utility hill, okay? They're all called indifference curves. This is not the best picture because I should emphasize these curves can't cross, okay? But anyway, if you look at the topographical map, at this collection of indifference curves, even though you can't see the utility directly like you can in the 3D picture, this gives you an idea of the consumer's preferences, okay? This is really the standard kind of picture that we would use, and in multi-dimensional choice models, that's what we'll be drawing, okay? So I've said enough about the consumer in this installment. I'm going to say more in the next installment, and we'll go through a parameterized example.